Hi, let us continue with our discussions related to the design of reinforced concrete peg footing subjected to the axial load together with the moment acting in both axes. So far, we have done proposing the size of the peg footing, making sure that the surface soil pressure does not exceed the soil bearing capacity where the peg footing is sitting on. This is important to prevent settlements of the peg footing that can affect the integrity of the structure. Next, we will enter the structural design part of the peg footing. According to the prescriptive methods, the structural design will be based on the ultimate limit state. The structural design will be related to the design of the moment resistance as well as the shear resistance. Therefore, we will need to determine the ultimate soil pressure. We will use the same set of equations that you use to determine the soil pressure, except now the loadings is in the mode of the ultimate limit state. You will use the ultimate axial load, which is 1000 kN, ultimate moment in both axes, which is 150 kN/meter, and also the ultimate self-weight. We calculate the self-weight based on the volume of the peg footing multiply the unit weight. That gives you 82.8 kN. Self-weight is a permanent action. Multiply the factor of safety of 1.35. That gives you the ultimate weight. And then the A, the Y, and the I are geometrical properties, which we have calculated earlier on while determining the surface soil pressure. The A is the contact surface area between the peg footing and the soil, which is calculated by multiplying 2.4 and 2.4, giving you 5.76 meters square. The Y referring to the centroid, where the moment rotations occurs. They are determined by having the width of the peg footing divided by 2. For the major axis, the HF is divided by 2. As for the minor axis, the BF is divided by 2. Since the proposed peg footing is square in shape, the centroid in both major and the minor axis, it will be the same. Same goes to the moment of inertia, which is calculated based on the equations BH power of 3 divided by 12. After that, you will obtain the P maximum and P minimum due to the influence of the moment, leading you the soil pressure something like this in the major and in the minor axis. The maximum stress is 258.1, whereas the minimum stress is 127.9 kN per meter square. Now that you have the ultimate soil pressure both in the major and the minor axis, you need the stress at the face of the column in order to determine the resultant force due to the stress, for you to compute the moment and shear acting on the surface of the column. For you to determine the stress on the column surface, you need to first find the locations of the surface of the column so that you can do interpolations from the changes of the stress due to the soil pressure. Therefore, we will need to determine the Z1 and the Y1. Z1 is calculated by taking the width of the peg footing, which is 2.4 meter, minus the width of the column, which in the major axis is equal to 300 mm, and then divided by 2. That gives you Z1 equals to 1050 mm. You will do the same for the minor axis. Take the width of the pad footing in the minor axis, which is 2.4 meter, minus the width of the column, which is 150 mm, divided by 2. Due to the smaller width of the column in the minor axis as compared to the major axis, your Y1 it will be slightly larger than your Z1. Once you have identified the Z1 and the Y1, you can now do interpolations for you to get your PZ and the PY. Take the maximum stress and the minimum stress, which are locating here. Assuming the stress changes linearly, and interpolate to obtain the PZ, giving you 201.1 kN per meter square. Same goes to the minor axis. Next, we need to determine the moment acting on the column face. This is calculated by converting the stress here into resultant force, multiply the lever arm. If you see the stress, P max Z equals to 258.1 kN per meter square, and then PZ equals to 201.1 kN per meter square. The stress appears in the trapezoidal shape. Get the area of the stress, and the centroid of the area, it will be the locations of the resultant force. To make it easy, the trapezoidal stress area can be separated into a rectangular shape and a triangle shape. Find the area of the rectangle, you get the resultant force. Multiply the lever arm, you get the moment due to the rectangular shape. You will do the same for the triangle stress. Take 201.1 kN per meter square, which is this stress, multiply Z1, giving you the area of the stress. That is the resultant force F2 here. Take F2, multiply the lever arm, which is Z1 divided by 2. That will give you the moment in these directions. And then you will do the same for the triangular stress. Take the P max here, minus the PZ. That will be this height. Multiply Z1, which is the base of the triangle. Multiply 1 by 2 to get the area of the triangle. The area of the triangle, it will be the resultant force for the triangle, which is F1. The resultant force will add at 2/3 the distance from the base. That means this lever arm here shall be taken as the Z1 multiply 2/3. That will give you the moment, which is equals to F1 multiply X1 plus F2 multiply X2. You will do the same for the minor axis, which for you to calculate the F2, you use this 197.1 kN per meter square, multiply Y1, and then multiply the lever arm, which is Y1 divided by 2. And then find this height. which is equals to 258.1 minus 197.1. Multiply y1 and then multiply 0.5, giving you the area of the triangle. Multiply the lever arm that is located at 2/3 of the base from the surface of the column. You will get two different moments in the major and the minor axis. The moment that you calculated from the area here represent the moment per unit width. You're going to multiply with the width of the peg footing in order to obtain the total moment. In the major axis, this will be the width. Take the moment here, multiply the width here. As for the minor axis, this will be the width. Take the moment, multiply the width here, you get this. Since the proposed peg footing is square in shape, the width B here for the major and the minor axis will be the same. That will be 2.4 meter. Later, you will use this to design for the moment resistance. In order to do so, we need to first determine the effective depth in both the major and the minor axis. The effective depth is determined from the top surface of the peg footing to the centroid of the reinforcement bar. This is calculated from the thickness of the peg footing minus the concrete cover minus half of the bar size of the reinforcement in the major axis, as expressed in the equation here. And then for the minor axis, you will take the thickness of the peg footing minus the concrete cover minus the bar size of the main reinforcement, and then minus half of the bar size of the secondary reinforcement. In this case, the thickness of the peg footing is 575 mm. The calculated concrete cover is 50 mm, and the reinforcement in the major and the minor axis are both 12 mm. You will get the effective depth of 519 and 507 mm for the major and the minor axis. Next, you need to get the K. Take the moment divided by FCK. The FCK is equals to 30 as given in the question, divided by the B, which is 2.4 meter, and then divided by D square, which is the effective depth. Remember to square the effective depth. This gives you the K of 0.016 and 0.02. Both Ks are less than 0.167, and therefore you know that no compression rebar is required. And then use the K, apply into the equations to determine the lever arm. You get your Z equals to 0.986 and 0.982 D. Both of them are greater than 0.95. Therefore, we will cap it at 0.95 D, which gives you the Z equals to 493.1 and 481.7 mm. Now it is time for you to calculate the AS required. Take the moment from the major and the minor axis. Take the Z from the major and the minor axis. Use the FYK, which in this case is 500 Newton per mm square. You get the AS required. 14 something and 17 something. You're going to propose sufficient amount of reinforcement bar so that the AS provided is greater than the AS required. Let's say we make a slim pass. 14 units of H12 and 16 units of H12 in the major and the minor axis respectively. You have your AS provided greater than the AS required. That means the proposed amount of reinforcement bar is adequate to take the moment. Later, you're going to check for the AS maximum and AS minimum. Checking the AS maximum is easier. We are talking about 4% of the concrete cross-sectional area. The AC here is calculated by having the thickness of the pad footing multiply the width of the pad footing. Since the pad footing is the same in both the major and the minor axis, the AC is calculated by multiplying the 2.4 with 0.575. As for the minor axis, it will be the same. The AS maximum calculated, you compare with the AS provided. The AS provided does not exceed the AS maximum. That means the pad footing is not overly reinforced. Next, we will look into the AS minimum. The purpose of the AS minimum is to control cracking. There are two ways to determine the AS minimum. One is through the formula given in Eurocode. Another one is determined by a factor based on the concrete grade. We are using grade 30 concrete, therefore we are talking about 0.0015 times BD. B is equals to 2.4 meter. The D we have calculated earlier on. You get the AS mean, and then you calculate the formula to get another AS mean. This you will require the FCTM that you can obtain from Eurocode table 3.1. A grade 30 concrete will give you FCTM equals to 2.9. Take FYK equals to 500 and then multiply the BD. The B is 2.4 in both axes. The D is the one that we have calculated previously. This gives you the AS mean based on the formula. Compare the two AS mean. The greater value will be the AS mean that we're going to use. We have confirmed the AS mean here. Check with the AS provided. It seems that the AS provided that we have proposed previously is insufficient. That means the reinforcement may not be effective in controlling the crack, even though it provides sufficient resistance to the moment. Therefore, we will need to increase the amount of reinforcement bar so that now your AS provided is greater than the AS minimum, and also at the same time the AS provided is more than the AS required. And also make sure that the AS provided not to be greater than the AS maximum. Only then you can conclude the amount of reinforcement. Once complete designing the moment resistance, later we're going to check for the shear resistance of the pad footing. This we will discuss in the following videos. Stay tuned.